All right, folks, this is a review of test 10. The question reads, if f is equal to ax squared when x is less than or equal to 1, or bx plus 3 when x is greater than 1, for which values of a and b is the function differentiable? So this is a differentiability to point question. Why? Because ax squared, which is quadratic, is differentiable everywhere, and bx plus 3, which is linear, is differentiable anywhere. So the only place you have to even ask yourself, is this differentiable, is at x equals 1. Differentiability to point. How do you test for differentiality point? There's two tests. First, continuity is the precondition, so the limit as x approaches 1 of f of x must equal f of 1, and that further subdivides into the limit as x approaches 1 from the left of f of x must equal the limit as x approaches 1 from the right of f of x. That affects the left-hand side. F of 1 isn't affected. Assuming you get all of this to work out, boom, then you are continuous at a point. That's the first condition. Second condition on you for differentiability to point is that the left-hand derivative equals the right-hand derivative at 1. So in other words, f prime from the left is equal to f prime from the right of 1. Okay, these two conditions, and you have differentiability to point. So we begin with the continuity question. The limit as x approaches 1 from the left of f of x has to equal the limit as x approaches 1 from the right of f of x, which has to equal f of 1. I've written that out here. Now using plug and chug, what do you get? You got a. Using plug and chug over here, what do you got? You got b plus 3, and here you just got a. So a equals b plus 3 is our first condition. So first we have to come up with a derivative function. So you just differentiate by pieces. When you have a piecewise defined function, you differentiate the pieces. So we get f prime of x equals 2ax when x is less than 1, not equal to 1. And f prime of x equals b when x is greater than 1. So we know that 2a must equal b, right? Plug in 1 for x here. Plug in 1 for x here. Not going to affect it. You get 2a equals b. This is the left-hand derivative equaling the right-hand derivative. Now you put the two of these things together. And if you put the two of these things together, what do you get? You get that a must equal -3 and b must equal -6. And that's the answer to number 1. All right, number 2 says the limit as x approaches 0 of 6x squared over 3 sine of 4x. You ask yourself how you would handle this problem. Well, you always start a limit by plugging and chugging. You plug in, you get 0 over 0, which is an indeterminate form, which means I can use, if 0 is 0 or infinity over infinity, L'Hopital's rule. So this becomes the limit as x approaches 0 of 12x over 3 times cosine of 4x times 4. Okay. And that's going to equal 0 over, well, cosine of 0 is 1, so this is 12, so this is equal to 0. All right, question 3, we're supposed to decide which one's even. All right, well, if you don't know any better, like for this first one here, you probably just do the test for even. F of -x equals sine of cosine of -x. Now you say, I know cosine's even, therefore this is the same as sine of cosine of x, and then I notice, oh, that's the same as f of x. So the whole thing turned out to be even by that definition, that f of -x equals f of x. Now I'm pretty sure I have my answer, but I go ahead and test the rest. Again, I don't know this one, so I'm just going to plug in f of -x. I get sine of -x cubed, which is the same as sine of x, -x cubed. Sine I know is odd, therefore sine of -x cubed is the same as negative sine of x cubed, which is negative f of x. Negative f of -x equals negative f of x. What is that? That's odd. Okay, now these two here, these last two, are neither, and here's why I'll tell you. Well, you know that this is the absolute value function, but what if you have the +2 inside of a function, it moves it to the left? There's no way that's symmetric about the y-axis. It's certainly not origin symmetry. Same thing goes on here, right? If this was just x squared, we know it would look like this. but plus 1 inside of a function shifts it to the left. So now it looks like this. There's no way that's symmetric about the x-axis or origin y-axis or symmetry around the origin. There's no way. So the answer is clearly then even. That's how you justify a problem like that. All right, question number 4 says, which of the following functions is continuous but not differentiable? Okay, well, I would draw them. Y equals the absolute value of x over x. All right, this one is the one that looks like this. Okay, clearly that's not even continuous. It's not continuous or not differentiable. And this one is y is equal to x minus 2 over x squared. Well, let's see. We know there's a rational function, and so we know that there's vertical asymptotes occurring whenever the denominator has zeros, and that occurs when x equals 0. Okay, so there's clearly a discontinuity. A vertical asymptote is an infinite discontinuity. This is not even continuous. So there's no way this thing is continuous but not differentiable at x equals 0. Next guy over here, we got y is equal to x to the 2/3 plus 5. Well, you just got to kind of know what x to 2/3 looks like. It's this function. It's got this cusp going on right here. It's continuous, and it's got a cusp going on right here. The plus 5, what does it do? It just shifts the thing up by 5. So it's going to look like this. All right? Plus 5 outside of function means we got this function here. Still got the cusp at x equals 0. So this thing is clearly continuous, but not differentiable. Why? Because the function is not differentiable when the left-hand derivative is different than the right-hand derivative, which happens at a cusp. So that's your answer. Let's just check out the last one. The last one says y is equal to 5x squared. This thing is continuous and differentiable. I mean, come on. That's a continuous differentiable polynomial. So the answer had to be C. Question 5, we got to find the area of a region bounded by a bunch of functions. Okay, so we're bounded by x, e to the x, which we might not know what that looks like, e to the x, which we definitely know what that looks like, y is equal to e to the x. We know this one, okay? The y-axis, which is right here. All right, and it's in the first quadrant, which means it's also kind of bounded by the x-axis, right? So we're looking over here, and we're like, okay, we got some boundaries that we know are going to be part of this thing. But what about the rest? So x e to the x, what does that look like? I don't even know where to start. Let's chart some points. Y of 0 is equal to 0 times e to the 0, which is 0 times 1, or 0. Okay, so I know, here I'll do a different color. I know that that's one of my ordered pairs. How about y of 1? Well, this would be 1 e to the 1, which equals what? E? And e is approximately 2.718. Okay. Well, I don't even know where that compares to the other function. So the other function, if I had y of 1, that would be e to the 1, which again is e. Oh, they match up at 1. So at 1 comma e, there's a matchup of some sort. That's an interesting find, right? All right, so the question is, what's going to happen in the middle? Like, which ones? Maybe it's going to be something like this. Maybe that's what we're looking at here. What was y of 0? Y of 0 would have been e to the 0th power, which is 1, okay, which is clearly greater than 0. So I would say this is probably our shaded region right here. It's a guess, but it's probably an educated guess. All right, so if this is our region, we find the area. We know how to do this. You basically find the area of this subrectangle, which is a base dx, and a height of the y top minus y bottom, right? And that gets you the area. So the area of the subrectangle is equal to y top minus y bottom dx. And in dx, y top looks like it's e to the x. Y bottom looks like x e to the x dx. Therefore, the area of the whole region, R, is going to be e to the x minus x e to the x dx. Definite integral from x equals 0. It looks like to x equals 1, right? That's 0. We already established that's 1. All right. Now we have the tricky part, which is actually solving this integral. Well, this one's easy to solve, but this integral here, x e to the x, how do you solve that? You'd have to use by parts on that part. Break up the integral here and then use by parts on this chunk. Oof. All right, so what's going to be what? U is going to equal x, du will equal dx. dv is whatever was left over, which is e to the x dx. And that means that v equals e to the x. And then, you plug in uv minus v du. So, if we were to continue this process, we could say that this thing is equal to, here, turn it back to black, this thing is equal to e to the x minus x e to the x minus e to the x. That's the by parts chunk right there. When x equals 0 to x equals 1, which if you do that out, you'll get e minus 2 units squared. All right, the hardest part here was actually by parts. Maybe it was trying to figure out which one was on top and which one was on bottom of these two functions. But the other part is this by part section right here. Okay. All right, so now we've got something over here. We get a suspicion this integral is something like arctangent of x, right? We get a suspicion it's something like arctangent of x plus c. But we know there must be something else to it. So the first thing we need to do is rewrite this thing as dx over, it's just like square roots of 2 squared plus 3x squared. Is that right? Square roots of 2 squared is 2. 3x, the whole thing squared is 9x squared. Okay. So now it's not quite of the form 1 plus x squared, right? It's not quite of that form. This is one of those modified forms where you really have to play with it. So let's say we didn't memorize the formula. And we're like, oh, I don't know. Was it this coefficient, this coefficient? I don't know. Maybe you go, it's that coefficient over this coefficient, x. Well, you test this out and you find out if you're off by a factor of square roots of 2, so you come back and say, oh, it must have been over that. Okay. So if you messed around long enough, you found this. 1 over square roots of 2 arctangent of 3 square roots of 2x plus c. Or if you just simply memorize the rule very well, then you got it. Okay, question number 7 says, let y is equal to x, 2 sine of x. Use logarithmic differentiation. You'd have to. This is fundamentally x to the x. That's not a power function. It's not an exponential function. You have no rule for its differentiation. So logarithmic differentiation says take the natural log of both sides. In theory, you could take the log based anything of both sides, but why would you choose a hard log? Use natural log on both sides. Now, the trick here is whenever you have natural log of x to some power a, you could bring the a to the front. So you get 2 sine of x natural log of x. All right, next we ddx both sides. So we get 1 over y dy dx plus differentiation. This is a product of functions, so you're going to get 2 sine of x, my first, times derivative of the second, plus the second times the derivative of the first. Okay, great. Now you want dy dx by itself, so you multiply both sides by y, and so you get 2 sine of x over x plus 2 natural log of x cosine of x times y. But you don't like 3 variables in here. I mean, it's not the worst thing in the world, but you want 2 variables. So you just rewrite what you got. And then in place of y, you put what y originally was, right? That's y in terms of x. Beautiful. Problem 8 asks us to anti-differentiate this integral. It's classic U substitution. Look at the composite portion, find the inner, and that's your U. Oops. Therefore, du dx is equal to 3x squared, which implies, of course, that 1/3 du is equal to x squared dx. Now you just plug and chug, right? So starting from here, going down equals, that's 1/3 integral du, and this is u to the 1/2 power, square root of u, 1 u to the 1/2 power. Okay, that becomes 1/3 times, get this right, 2/3 u to the 3/2. Make sure you integrate, not differentiate. All right, add 1, plus c, and then convert it back. This is 2/9. U was right here, x cubed minus 1 to the 3/2 plus c, and that's your answer. All right, number 9 was a gimme. We got y is equal to x squared e to the x plus 3, and you're asked to differentiate. Okay, fine. So it's a product of functions. So let's do it. First times the derivative of the second, which theoretically is chain rule. It's derivative of the outer with respect to the inner times the derivative of the inner. It doesn't really affect it. First derivative of the second plus the second times the derivative of the first. That's it. Okay. And if you wanted to be happy about it, you certainly could write, if you wanted to, y is equal to e to the x plus 3 x squared plus 2x, if that makes you happy. All right, number 10 asks the limit as x approaches 0 of tangent of x over x. The first thing you do with the limit is you plug and chug. You get 0 over 0. This is an indeterminate form that qualifies for L'Hopital's. So this means that we get the limit as x approaches 0 of derivative of tangent is secant squared of x. Derivative of x is 1. Okay, so then you plug in 0 here and you get 1. All right, number 11 says, let R be the region of the first quadrant bounded by y equals x squared. You know what that looks like. The x-axis. The first quadrant between this guy and the x-axis over 0 to 1. Well, it's 1. That's a 0. So we must be talking about this region right here. See that? All right, good. Now part A says find the volume of the solid formed by revolving R about the x-axis. So we could take R and revolve it around the x-axis. Okay, revolving around the x-axis, everything's going to be in what? X dx. And you should be able to make your cuts in x. And if you make your cuts in x, let's change the color here. Change the color here. It should be the disk that you're creating right there. You see it? Okay, the radius, of course, is going to be this upper chunk, the chunk that's taking place where? The shaded region. Okay, so the volume of the disk, it's pi r squared h, which is the same as pi times, got to find out what this radius is, and that's dx. I think obviously tell it's dx, and everything is in xxx dx, no question about it. So what's the radius? Well, the radius, you can see right here, this radius right here is y top minus y bottom. Would you agree? Y top minus y bottom. All right, great. Y top minus y bottom. But I don't want it in y, I want it in x. So it's pi times, what's y top? X squared. What's y bottom? 0. So this is no different than pi x to the 4th dx. Now for the volume of the shape, this should be easy. Definite integral from x equals 0 to x equals whatever this is, which was 1, of pi x to the 4th dx. So you run this and you get pi over 5 units cubed. Make sure you integrate properly. Don't differentiate, integrate. Okay. Part B then asks us to do what? Part B asks us to find the volume of the solid if you revolve around the y-axis. So now I don't care about any of this down here. That was gone in this problem here. Now I'm going to revolve around the y-axis. So I'm up here doing my revolution, not here anymore. I'm up here doing my revolution. So now my shape becomes this. All right, now, what is this thing? What is this thing? Oh, wait, I notice it's a disk problem. Hopefully you see the outer disk. not the greatest picture. There's also an inner disk. Hopefully you see that inner disk right there. Not the best looking inner disk. All right, so the volume of the washer is going to be pi big R squared minus little r squared h, which equals pi times, we just got to find what that big R squared is, and we got to find what the little r squared is, and it's going to be what, dx or dy? Dy. How do you know that? You revolved around the y-axis. Also, you make your cuts in y, so you can clearly see that this thing right here is dy, but it's revolved around the y-axis. It's good enough for you. All right, let's talk about the big radius. Which side do I look on? The shaded side or the non-shaded side? Clear the shaded side. So here is my big radius, big R, right? What is that? That's x on the right minus what? X on the left. But I don't want it in x, I want it in y. So what's my x on the right? 1. What's my x on the left? 0. That equals 1. Now we do the same thing, right? We do the same thing over here with little radius. It's going to be little radius. It's going to be x on the right minus x on the left. Well, what's x on the right going to be now? It's no longer 1. Now it's, get it from here, it's x equals the square roots of y. On the right, it's 0. So again, this thing becomes the square roots of y. So, right, going back over here, we said that the big radius was 1 and the little radius was square roots of y. That in turn is equal to pi times 1 minus y dy. That seems to be bad at all. So the volume of the shape then is definite integral from y equals something to y equals something with pi times 1 minus y dy. Well, what in the world are we talking about here? We're talking about y equals, looks like here, which is 0, up to here, which is, well, if x equals 1, then y equals 1. So 0 to 1. And that in turn is going to equal pi over 2 by units cubed. All right, question 12 is a throwback question to rational functions. So we got 2x plus 4 over x squared minus 5x plus 4. Before we do anything else, we just say, okay, you know how to do this. What are the zeros? It's where the numerator equals 0. So that's x equals negative 2? Yeah. And then the vertical asymptotes are where the denominator equals 0. Well, that's where 0 is equal to x squared minus 5x plus 4, which is the same as 0 is equal to x minus 4 times x minus 1. Foil it out, that's correct. Therefore, x is equal to 1 or 4. Those are my vertical aspects. You got to write them out like this. X equal to 1, x equal to 4. By the way, is this 0 crossing or touching? Well, it's got a multiplicity of 1. See? So it's a crossing. How about these aspects down here? Well, clearly they have a multiplicity of 1 and a multiplicity of 1. So that means we're what? Volcano or opposite? Opposite and opposite. All right. Now the only thing that you last have to talk about is horizontal asymptotes. How do you do that? You take the limit as x approaches what? Positive or negative infinity of f of x, which is just the same as the limit as x approaches infinity of the top power of each, right? Which is just really, you got 2x over x squared. Y. This is clearly 0, okay? Which means y equals 0 is the asymptote, horizontal asymptote. So now we just draw this thing. No problem. No problem at all. Let's draw it. Now let's say we have a 0 at, where do we say, negative 2. Okay. And we've got vertical asymptotes at 1 and 4. That's x equals 1. This is x equals 4. Give me 10 seconds. Okay? And then we know we got a horizontal asymptote at y equals 0, another horizontal asymptote at y equals 0. You might want to label this vertical asymptote 0, and horizontal asymptote. And the last thing you do is draw this in. Well, you test any region. Testing 0 is the easier. If you test 0, you get a positive number. So this was positive. It's a crossing 0. It's got to double back to our asymptote. This was opposite, so we got to be down here. And we got opposite, so we got to be up here. And then to the asymptote, and that's it. That's what you get. All right.